welcome back. So today Professor Mattila is going to give his third lecture in the series. Continue with this.
Yeah, thank you very much. Okay, so today I will talk about a problem for which I did something 40 years ago, and now recently I did something more, but I didn't spend the last 40 years thinking about it. I was hoping and waiting that somebody else would do some more. When nobody did, then I thought I should have a look at it again. So the problem is that if I look at two sets in Rn or in the plane, they are just arbitrary Borel sets A and B, and I take one of them, I rotate and translate, so I apply Euclidean transformations. Then what can I say about the dimension of this set? Its intersection. For essentially completely arbitrary sets. But before going into this, I look at the special case where B is a plane. So then we have, for example, in the plane we have Marstrand's projection theorem, which says that if A has dimension bigger than 1, then if we project here, this projected set has positive one-dimensional measure, and therefore orthogonal lines in a set of positive measure meet this set at some points. And now, in this case, the question is in how many points, in how big a set do they meet?
Just for the notation, I mean, this B is any arbitrary set?
Sorry?
B, what is B?
A and B are both,
Okay, any arbitrary set. Okay.
yeah, Borel. G is an orthogonal transformation, and Z is a translation vector. But first, B is a plane. So then we have a theorem due to Marstrand from 1954 from the same papers. His projection theorem. Well, he did it in the plane, and I did it higher dimensional version in 75. So if S is bigger than an integer m, and I have S-dimensional Hausdorff measure of A positive and finite, you can find a formulation of this result also for, if I just talk about the dimension, but it's more precise information when I make this assumption, which is not really restrictive. Then for almost all V in Gn, no, G in n minus m. So this is the Grassmannian manifold, the set of linear n minus m dimensional subspaces of Rn. Almost all means to the natural orthogonally invariant measure on that. So if we are on the line, it's just a one-dimensional measure on the lines through the origin. Dimension, the set of U in the orthogonal complement where dimension of A intersection V plus U is S minus M. This is positive. This has positive m-dimensional Lebesgue measure. So this is an m-dimensional space, and then we have the result that positively many of those planes intersect in this. Now, what I would like to do first is to give a generalization, very general version of this, which applies then to many other situations. It gives that and many other things. So I consider almost arbitrary family of orthogonal projections. So P lambda goes from Rn to Rm, but you can think that these are orthogonal projections to M planes in Rn, and then you just identify each Rm with Rm. So it's better to think about it as a mappings to Rm. So these are orthogonal projections, and lambda is in some parameter set capital lambda, which is a compact metric space. So in this situation, it is just this Grassmannian. And then I have omega is a Borel probability measure on lambda. And this is essentially all, except that I have to assume some measurability. So for example, that the map which sends lambda to P lambda x is Borel for every x in Rn. So this is just that I have a lot of integrations, I use a Fubini's theorem and so on, and I need some measurability for those, and this is just for measurability purposes. Sorry?
What is big lambda? What is big lambda?
This is a compact metric space. Some arbitrary compact metric space. And then I have the theorem which says that I maybe use some numbers for these theorems, maybe I will refer to them. Suppose P is a number bigger than 1 and S is bigger than M. M is the range of those projections. And there is some constant C such that, and now what I'm assuming is that the projection theorem is true. But that's not quite enough just to assume that sets of a dimension M project to sets of positive measure. I need a quantitative version of this projection theorem. And the quantitative version says that that for omega almost to lambda in capital lambda, first of all P lambda mu, I will say soon what mu is absolutely continuous with respect to the Lebesgue measure. And moreover, then I can consider it as a function, and if I take this function and I take its LP norm, P lambda mu, I raise it to the power P, and I integrate, so this is living in Rm, I integrate over Rm, and then I integrate this with respect to this measure omega over this capital lambda. So I assume that this has a bound this constant, which I assume to exist, mu measure of the unit ball in Rn. And when is this supposed to happen? It's supposed to happen when mu is an S. Frostman measure on the unit ball in Rn. Mu is a positive and finite Borel measure in the unit ball in Rn, which satisfies the Frostman condition with exponent S. So it is supported, it lives on unit ball. So all this is my assumption, and this is a quantitative, so this means that I'm assuming that the quantitative version of the projection theorem is true. And for example, in the proof I gave for Marstrand's projection theorem that was only on in the plane, one can read from this proof that actually this assumption is true. And it is true in many other cases. So this can be usually applied if you have a projection theorem saying that sets of dimension bigger than M projectus, positive measure almost always, then you often can, if you look at the proof, you can get something like this. So then, if A in Rn is Borel and it has positive and finite S-dimensional measure, then for omega almost all lambda in capital lambda, I have this level set result. Lm of values of Z for which dimension of A intersection P lambda minus 1. So this is an n minus m dimensional plane. Z equals S minus M. This is positive. So I have a quantitative version of the projection theorem, then I can conclude the result on the sections that many of these planes have the expected dimension, because that's what one should expect. I don't say very much about the proof, but I apply the assumptions to measures nu rho, where nu rho is obtained so that I first take a measure mu rho, which is rho to the minus 1 s. So I take this scaling and mu restricted to S-dimensional Hausdorff measure restricted to BAR. And I have to, well, I don't write it because it's not so essential, but I can assume that this Hausdorff measure satisfies this Frostman inequality. If not, then I go to a large subset which always exists where it satisfies. So I assume that this measure is S Frostman, which I can easily get. This is rho. So I restrict this measure to this little ball, and then I scale it back to the unit ball. So nu rho is then T a rho mu rho. So it's a push forward under this, where p a rho x is x minus a rho. So what's happening is that I have in a little ball, and when I prove this theorem, I use some covering arguments to get coverings with little balls. And in each little ball, I apply this result, and I apply it to this scaled version of mu, not only the restriction. And this is the map T A rho, which sends this ball to the unit ball, and then nu rho lives here. And it is an S-Frossman measure on this ball, as you can check. So why do I do the scaling? Because now, if I look at the p lambda mu r, mu rho, I take the LP norm of this for any lambda, so I integrate over Rm. Then you can check from the scaling what happens, and what happens is that you have rho to the power m plus p s minus m integral No, I think I take away rho to the minus s from here. So this is just the restriction, and then I take rho to the minus s here. So it is the same result, but then when I write nu rho, it should be like this. So mu rho is just a restriction. So if I look at mu rho of p lambda mu rho to the power p and integrate over Rm, then I get this. So the essential thing is that I get some number here from the scaling. And then I have covering arguments with balls of different radii, and I have to sum up the radii raised to the certain power where this number appears and something else appears, and the final number should be positive because I essentially apply it to rho equals 2 to the minus j. And it happens that when I have this number, then I will get in the end positive. So I only wanted to say this because this is the reason why this argument works. And essentially, it should work much more generally. So, I mean, I could look at some other transformations, some nonlinear transformations or something, and hope something like this. And everything else should go through in much greater generality. But here, when I project to this plane V, then when I look at these projections, I look at these intersecting planes, then when I make this transformation, I get exactly the same kind of lines here. If I would use some nonlinear versions, then I wouldn't have this, and when I would do the scaling, I would have something else, and it wouldn't anymore be in the same situation where I am making my assumptions. So that's the reason why this argument seems to work only for linear mappings. But once we have this, we can come back to this problem. Well, no, maybe not yet, because, so I said this applies to get theorem 1, which is not a great deal because the proof is not simpler than the original proof. But it applies also to some restricted projections. And this is mainly due to Terence Harris from something like 2022 to 24. He has several papers where he has something like this. So I tell you more concretely. I mentioned in R3 these restricted projections where you take projections on the unit sphere to some unit vectors generated by a curve in the unit sphere. So if I, for example, take p lambda orthogonal projection onto p cosine lambda sine lambda 1. These in Rn, so I have, this is a line, well, no, better to say T is in Rn here. And then lambda could be on 0, 1, for example. So I have this family of projections generated by these lines going through these points on the curve in the sphere. Or I could also take it to be if I call this gamma lambda, then I could also take it to be projection to the plane, which is orthogonal to this vector. So in these cases, Harris has these quantitative projection results. And there he needs P different from 2. 2 is the most natural choice. So actually I first proved this with this result with P equals 2, and then Harris remarked that it would be better to have it P for more general P, and he had some argument also, which I then used. And he has also this kind of result in Heisenberg group for certain families of lines. So one can apply it in many situations, but one cannot apply this yet to this intersection problem I'm really talking about. Because there I have two sets. So I have to modify this. So theorem T says that I have two positive numbers, S and T, and their sum is bigger than n. And now these projections P lambda go from R2n to Rn. I could take some more general dimensions, but this is the situation where I'm applying this. And then this condition is replaced by P lambda of product measure mu cross nu. And P lambda mu cross nu here. And then I need also the unit ball with respect to nu. So I have two measures, and both of them now live in the unit ball of Rn, and nu satisfies the Frossman condition with exponent t. Then if I have two sets A and B, which are Borel sets, and
Actually, on the right-hand side, you don't
sorry,
have a new term at all.
sorry.
So, on the up. So when you are writing down that inequality of them, so you don't have any play of new there. Mu is another measure that you're looking at.
The product measure, I mean,
Yeah, but I mean, so I mean, on the right hand side, you only have got mu.
You,
mu and nu.
where on the right hand side?
Now, on the right hand side, C times mu of.
Mu into mu. Mu of B and B.
Ah,
I don't see.
Yeah.
it's okay.
Is it okay?
That's new.
That's new. It's not the union. It's not equal.
Oh, I see. Maybe. So I'm making this assumption with two measures, and then it concerns the LP integral of this product measure, and then I have t-dimensional set B and s-dimensional set A. And then for almost all lambda, I don't have quite this. I have greater than equal to s plus t minus n. And in general, one cannot get this, because what one could get is somehow instead of this, the dimension of the Cartesian product, dimension of A cross dimension B. And one has this equality if dimension of the Cartesian product is s plus t. But it is not always. But it is, for example, if A or B is AD regular, which means that measures of balls, Hausdorff measures of balls behave like R to the S or R to the T. So for very class family of sets, I have equality, but not all, and it is not true for all. And I still have to have here A cross B. So then the proof is quite similar, and I can get this product set version. And this can be applied to this intersection problem. And how? Well, so I have to interpret these intersections as level sets.
So what is this equality of this distribution function?
Sorry?
Dimension of- What is the equality? No, it's not very clear to me. So now we are estimating this distribution function in project Rn, right?
Yeah.
And then if dimension of A cross B equal to S plus T,
Then you have equality here.
oh,
Then
the
you can
dimension
put
of
equality.
A cross B intersection with the projection is equal to S plus
Equal to S plus T minus N. But in general, you don't have equality. So in the previous theorem, when I have only one set, I had equality here. But now the equality would mean that I would take here somehow the dimension. In place of this, I would take the dimension of the Cartesian product. And that's not always the same as S plus T. But I want this because this is the version that's applied here. So let's look at the intersection of two sets. So I have here some set A. And then maybe here some set B. And now I want to consider Cartesian product of A and B. So I have B maybe somewhere here. And then the Cartesian product is this rectangle. So how do I get A intersection B from the Cartesian product? Well, I intersect it with the diagonal. And if the picture is correct, then this projects to A intersection B. And this you can check very easily. That you take diagonal, intersect the Cartesian product, and project down, and you will have the intersection. Now if I want to move B, translate it, then it means that I translate this diagonal. I look at it different directions. And then from this you see that this intersection you can write as projection, and this pi is projection on the first coordinate of A cross B intersected with BG minus 1 of X, no, of Z. Where BG, so you can figure it out quite quickly what BG has to be. It has to be X, it takes XY to X minus GY. And this is actually essentially an orthogonal projection, as you can check, onto the plane, n plane in Rn x. I think it was minus G minus 1 x. X is in Rn. So this is an n plane. And this identity you just check, take one point here and check that it is here. There is nothing. So I can write these intersections as level set except for these projections. But I am projecting from this plane to the first coordinate, and this projection is just quite innocent there. It just changes all distances by a constant factor. Therefore, it doesn't change dimensions or anything like this. So this doesn't harm at all. So I can essentially forget it, and getting dimension results for this is the same as getting dimension results for these. And now I can apply this theorem. But it needs still that I have this condition for those particular projections generated by orthogonal transformations. So I need that if mu and nu are as in theorem 3, then integral p lambda mu cross nu, and now I take p equals 2, integrated over Rn with respect to the Lebesgue measure. So this again involves already the assumption that these are absolutely continuous, so I can consider them as functions, and then integrate it with respect to G, and this means the Haar measure on the orthogonal group. This is less than or equal to constant times mu Bn01 nu Bn01, where mu and nu satisfy, whenever mu and nu satisfies those conditions. So this should be checked, and yeah, BG, thank you. And well, in the other, well, I also have the projection theorem for these projections, not for product sets, but for general sets, giving quite sharp results what these projections do. And but for product sets, I get better results, and that's actually easier to prove, but it depends on some rather deep result. Or maybe I can essentially write the argument there. So what you do, I take the Fourier transform of this measure. And, well, it cannot be too hard to check what it is, because everything is very concrete. And what you get is Fourier transform of mu at psi, Fourier transform of nu at minus g minus 1 psi. So this you check from the formula of Fourier transform. Then I take this integral and write it in terms of the Fourier transform by Plancherel formula. So the first integral is over Rn. And I plug in this formula for the Fourier transform, so I will take first here mu hat psi squared, and then the rest is nu hat minus g minus 1 psi squared dg, and then d psi. Now here I integrate over the orthogonal group this kind of thing. And what happens, it's actually an integral over the sphere, because I integrate over this. So this is nothing but integral of nu hat. This is the kind of average I had earlier. Psi v squared over the unit sphere. And for example, this was the average for, I mentioned some estimates. So there was the first sharp estimate by Tom Wolf in the plane, and then there is an estimate that this is less than or equal to, with some constant, psi to the power minus n1 minus 1n t plus epsilon, but epsilon is arbitrary, so it doesn't harm here. So this estimate is here due to Du and Chang. It's quite recent, well, about 20 or something. And I mentioned it because with this estimate, they got new results on the distance set problem. But when you apply it here, you will get this. And then, then this will essentially lead to something that, but this will give you that this is finite, because the integral you will get from here is something like inertia of mu. Since you are left, when you plug in this here, you have mu hat psi squared, norm of psi to certain power, and that is an inertia integral of mu with certain exponent. And when you look at the exponent, you will get that will give you the finiteness under those conditions I had. So I didn't have the conditions. So this is if S plus n minus 1 over n p is bigger than n. So under this condition, using these, one gets this quantitative absolute continuity of the projections. So this argument is quite easy once you have this Duan-Chang inequality.
So just one maybe a silly. So from the estimate of the wall, how do and Sang are coming to the sphere?
Sorry?
Because what we know is that the mu of p r is lesser equal to r to the power s, t to the r to the power t.
Yeah.
From there, how they are coming to the sphere from the ball? Estimate.
How you get this estimate? Well, I mean, it was first done by Tom Wolfe in the plane, and it's not easy. He used the restriction theory argument, which had to be used earlier, and this is actually something they did in connection of the Schrödinger inequality equation, and then they took some arguments from that. And so it is not something you can see obviously that there is a connection, but it can be proved. So this is the deepest part of the proof actually. So, so we have that this condition for those projections, we have this theorem, so assumptions are valid, so we can conclude this, and we have this how those level sets correspond to the projections. Then that will give me the intersection theorem. Sorry? P larger than 2. Well, then this assumption is stronger. If P is larger than 2, then this is stronger. Then you can actually just... I mean, you don't usually get it for P larger than 2, but if you have this assumption with P larger than 2, you have it also with P equals 2, because this is a finite measure. Sorry? No, but I mean that if you have the assumption with P equals 2, you can actually just go to the case where P equals 2 and then forget about P bigger than 2. It doesn't give anything more, at least so far as I know. Well, yeah, the point is that that you should know this result with some P. If you know it with any P bigger than 1, then you can make this conclusion. And sometimes you know this with, for some families of projections, you know it with P equals 2. For some families, you know it only with some P less than 2, but bigger than 1, which is a weaker. Well, I don't know any case where you would know it for P bigger than 2, maybe there are such cases. But it's just essential that there exists one P bigger than 1, and then you can do this. So the value of P is 10. After that, it doesn't matter. So the intersection theorem says that I have S plus T bigger than N. But then I have more. S is bigger than N plus 1 over 2, or S plus N minus 1 over N T is bigger than N. So this is the case which I had there, and this is a stronger assumption than S plus T is bigger than 1. And I say it here so that I don't forget that S plus T alone, this condition should be enough. But that I don't know. This is a little bit the same as in Falconer's distance set conjecture, that if S and T are the same, then this is that S is bigger than N over 2, the same number. So this should be enough, but I only know it with these two separate assumptions, and neither of them implies the other, so they are distinct. But then if I have those, if A and B in Rn are Borel, A has positive and finite S-dimensional measure, B has positive and finite T-dimensional measure. Again, these assumptions would not be necessary. I could write it with just talking about the dimensions, but the statement would be less precise. I would have to subtract some epsilon here. But one can get a statement also without assuming that they have for some positive S and T positive and finite measure. So if I have this, then for almost all orthogonal transformations, Lebesgue measure of the set of translation vectors, so that the dimension of A intersection G of B plus Z is greater than or equal to S plus T minus N is positive. So you, for almost all right, when you have this, you have A and then you have B, then for almost all rotations of B, there is a positive measure set of translations where the intersection is that big. And again, it is the same as there. Equality holds if A or B, for example, is AD regular. So rather general sets holds equality, but not general. And that you get from that result. So a few comments still. So this was started around in the early 80s. And the first result said that if I don't only use here isometries, but also use dilations, so if I use almost all positive R and almost all rotations, you look at R, G, B plus Z and intersect with A. So I allow larger transformation group. Then I don't need this assumption. And this proof can be done completely without Fourier transform. But in this case, where I am orthogonal transformation, Fourier transform is used in several ways. So this was proved by Jean-Pierre Cahan and myself around 84, but it was not a joint paper. Unfortunately, I never had a joint paper with Jean-Pierre Cahan. So this was independently. We didn't know of each other when we did it. But this was the first result in that case, and then I started to think about if you have only isometrism, it means that you only have orthogonal transformations. And then still we have only these partial results, but we have something. And this is also true on the line. Then you don't have any rotations, you have only dilations. And it is true. But in the line, you don't have anything without well, this is not true on the line, which means that you leave out completely rotations. You only have translations. So there are examples that with only translations you don't get anything. There are A and B in Rn with full dimension, but Lebesgue measure 0. Such that if you take A and you translate it with any vector S, then this set contains at most one point. So they are big in dimension, but however you try to translate the other one, they never meet in more than one point.
What is Z?
For any translation.
Almost everywhere Z.
No, every set.
For every Z.
Every set. However you translate, they don't meet.
And this symbol is what?
Cardinality. Number of points in this set.
So now,
Number
if
of-
I take two intervals,
No, you don't take two intervals. There exist.
there exists. Oh,
There
okay,
exist.
okay.
Of course, for many sets.
Sure.
For many sets, this is completely wrong. Yeah. Sorry. Sorry.
When z is equal to 0, for all z belongs to Rn, z is equal to particular z is equal to 0.
Yeah, thank you. No, for all, because I have different sets. So if z is 0, it just means that A intersection B contains at most one point. So it's for all set.
Can you take them to be compact?
Z is equal to 0 and b is equal to a. But there exists.
There exists A and B.
There exists.
Yeah.
Can you make them compact?
Yeah, compact. Yeah, they're compact. Then about this opposite inequality, there is an example construction of Falconer which says that for every there is A in Rn of dimension S such that dimension of A intersection Fa equals S for every similarity transformation F, which means that you look at no, it was Maybe I don't remember correctly. I didn't check this. No, maybe this is not every, but for every. Well, anyway, it is true for every GA plus Z. For every G and Z, every isometry anyway. So I'm just saying that that this inequality can, the opposite inequality can fail very badly for general sets. This intersection can be as big as the dimension of A and B. Okay, so I stop here this time. Thank you very much. Sorry?
While giving the outline for the proof of theorem 4, you basically check the conditions in theorem 3, right?
Yeah.
But then the conclusion that would be that the dimension of A cross B intersection BG inverse of Z, maybe the dimension of that set is bigger than S plus K minus M.
Yeah.
You can have that for almost every Z.
Yeah. The project?
So A intersection G of 3 plus Z is the projection of A cross B intersection BG inverse of Z.
Yeah. No, I didn't understand the question.
No, maybe we can discuss it.
Yeah.
That's right. So inside this set, we are asking for something like a stronger condition. We are asking the dimension of the projection to be rather than S plus A plus M. That's right.
Yeah, and if you think about this projection of the first coordinate. Yeah, well, I mean, there is nothing happening because I looked at A cross B intersected with BG minus 1Z. And this thing is some plane. So this set is living on some n plane here. And when I project here, nothing really changes except from some fixed number.